I'm going to talk today about failing over without falling over. And many of us have seen systems that we built out, and we built in all the reliability systems, and we've got all the failover plans. But what happens in practice is that we end up in a big heap with everything broken. So why is that? And I'll just give a brief view of something we might be able to do about that. So to start off with, I like to ask people, do you have a backup data center? How often do you fail over apps to it? Get a few answers to that we're okay. How often do you fail over the whole data center at once? People typically get pretty embarrassed about that point. And I call this availability theater. If you've got a backup data center and you've never really failed over to it, or you're not confident that you could fail over to it in a moment's notice, you invested a lot of money for a sort of a facade of availability. And if we look at some data from the Uptime Institute, historically, most recorded outages have been because of power failure across all data centers for all sort of public reportings of outages that to do with IT. But more recently, the most recent report, they find that IT and network problems have moved into the lead, and they are now causing more failures than power problems. So why is this? Well, here's an interesting sort of book about this sort of type of failure. Failures result from an unanticipated interaction of multiple failures in a complex system. That's what we build. And Perrow calls these normal accidents because, yeah, they're unexpected, they're incomprehensible, they're uncontrollable, but they're also unavoidable. You're definitely going to get these, so that's why they are normal. You should regard them as a normal outcome and something that you should be trying to manage from. And because of this, we try to build redundancy into our system, so if something fails, we've got an alternative to fail over to. The problem is that the ability to fail over is actually sometimes more complex than the thing we're failing over. And then the overall complexity of the entire system is now much larger. And we built ourselves a more complex system, which is more likely to fail. And that's why the whole system quite often falls over. So how can we do better on this? I've been using this slide for a while because really, yeah, you can only be as strong as your weakest link, and you need dedicated teams, you need a security red team, you need a chaos engineering team to find those weak links. But this is actually sort of a little bit of the wrong analogy. So here's an update to it. Think about this as a cable or a rope. They have lots of strands. And if you get a few strands broken, the cable or rope still works. But after a while, you're down to the last few strands that are just enough to hold whatever the stress is on the rope. And when they break, then you've got a failure. And if you go into that and say, well, the cause of failure was the last few strands that broke, you're not really getting the big picture. Because what happened here is you build resilient systems that have lots and lots of redundancy in them, and you gradually use up that redundancy until your rope gets frayed and frayed until it actually breaks. And this is encapsulated in this great book that I've been recommending to people for a long time, Drift into Failure, which explains why this occurs. Everybody with the best intentions, locally optimizing at every step in the process, will gradually consume all of that safety margin until the system fails. So the way we have to work from this is to capture and learn from near misses and test and measure those safety margins before things go wrong. There's lots of good examples here in the airline industry. The slightest thing that goes wrong with a plane is recorded and reported to all of the airlines flying that model of plane, all of the aircraft flying that model of engine, whatever part of the system it is. So they've built in a global system across all companies to report on types of failure. We don't have that kind of thing in the software industry, in the IT industry, but that's an example of the way you need to think about this. Something Chris Pinkham said years ago, he was the original engineering manager for AWS EC2. He said, you can't legislate against failure, focus on fast detection and response. We've been talking a lot recently about observability. And observability is the detection part, but you've got to be able to respond in order to manage a failure. And you've got to be able to link the observability to the control, which means there's some kind of model in there which says, I'm looking at this, that means something, and here's the control response. This is a control system problem, and there's a lot of work that's gone on over a long time in safety critical systems. And I've been reading up and trying to learn from these people. My latest favorite book is Engineering a Safer World by Nancy Leveson of MIT. She's a professor at MIT, and you can go look at the handbook and the talks. They held an online conference earlier this year that I listened into quite a good amount of. Lots of great ideas here. This is not just about availability, it also covers cybersecurity and that aspect of safety. So there's a lot going on here, and I'm just going to give you a sort of a view of how I think we can apply this. So here's a diagram from the book. What we have is a human controller, an automated controller, and a control process. And the observability part is the sensors and displays. But there's also the controls and actuators. And then the other thing that's shown in here is a model of the control process in the automated controller. So that's quite often some code that you wrote that manages the system, or an auto-scaling group, the configuration, something like that. And the human controller, who also has a model of the automation and a model of the control process. If you think about how this can go wrong, if you think about the Boeing MAX 8 plane problem. The plane was the control process, the automated controller was the stall control system. They upgraded that system to have a new model, new way of working. And the human controllers, the pilots weren't trained in what to do, or even that this new model was there. So their model of automation was not in line with the actual automation. And that was one of the reasons why that plane became uncontrollable and crashed, because the human controllers didn't know what to do. Now, if we look instead at the kind of IT systems we build, I just relabeled this diagram. So we have the human controller who's watching the throughput of a system. Say the control plane is probably an autoscaler or something like that. And then there's a web service turning customer requests into completed action. So we sometimes call those the control plane and the data plane. What STPA does is it looks at the hazards that could disrupt this. So let's look through some of these hazards. On the sensor side, you could have missing updates, they could be zeroed, overflowed, all kinds of things can go wrong with your system. Coordination problems, software updates over time sometimes break the sensors or break the meaning of the sensors. And so you're not actually looking at something that, what you think you're looking at. Then there's problems with the model. Mismatch, you're not looking at the right inputs. The updates, we've all seen log files scrolling up the screen ridiculously quickly, so we can't see what's going on. Updates may be too infrequent, so you get an update every hour for something that's breaking by the second. Again, coordination problems, degradation over time, all kinds of things there. And then the human actions, maybe you're just not paying attention. Maybe you do unsafe things in the wrong order. Maybe there's more than one human controller that has a different idea about what to do because their models and the inputs they're seeing are not lined up. And so you get two controllers or operators trying to fix the system in different conflicting ways at the same time. And your run books are probably out of date, so that's a degradation over time. So if we look at this, it says at the bottom, disturbances. And what do we mean if there's a big enough disturbance to break this web service? So the control plane is there to manage small disturbances. So if you get a burst of requests, maybe it scales up. Maybe there's a bunch of fraudulent requests coming in and the control plane has some fraud analysis which will cut them out. So there's a number of things it does. So think of the control plane as managing the data plane, and there's a limit to what it can do. If you go beyond that limit, you are out of control. And so if your control plane automation failed, that code broke, you're out of control. But also things that are out of scope of the controller, like say a network partition, so the customers just aren't even getting to the system. That's out of the scope of the control system. And then places where the control system's working, but it cannot fix the system. Say the application crashed or corrupted its database and can't be restarted. So those are cases where the control plane cannot compensate for the disturbance. So what are we going to do about that? Well, one way of dealing with that is to provide a second system which can take over. So I sort of drew this diagram, stretched it out, reconnected it. So now what I've got is we have a control plane for the routing service, and then we have two more control planes for web service A, web service B, and we can switch between them. The problem here is there's a lot more to go wrong, much more complexity with a human controller to try and model. And so how can we deal with this? How can we make that better? One way to simplify the human model is to use patterns and symmetries. Symmetrical patterns are easier to understand, right? The more simple the pattern, the better. And that means that you can get your head around what's going because you understand it more easily. And then use tooling to enforce that symmetry. One of the things about moving from data center to cloud is you've got consistent automation, modern control planes, and cloud has useful symmetries built in because your automation is the same, your configuration as code means that your systems are built the same everywhere, and the instance type services, versions, zones, regions, there's a lot more consistency than you will ever find between two data centers, even if you're trying to keep the data centers in sync. So here's the principles. If it can be the same, make it look and act identically. Be careful to not introduce things to break the symmetry. Just maybe for, well, I don't really need two of these, so I'm going to optimize and make this one a little bit different. It's actually, from a resilience point of view, good to have them both be the same. If something is different, try not to paper it over and make it look the same because it's going to behave and fail in a different way. And then test those assumptions. This is the chaos engineering resilience test. You're testing the assumptions whether things really are the same and different, as well as other aspects of the failure. And one thing here is to kind of have three ways to succeed. Replicate over 3 zones in a region, or 3 region triple active if you're going across regions. And for really high value applications, sometimes you have 2 secondary regions to fail over to. So I redrew that diagram to be a bit simpler and have a 3-way replication. So this is the same general idea. If we look at the AWS Availability Zone model, what we have here, if you do it right, you have some symmetries. You want to have the same data. So all data should exist in all 3 zones. All services should exist in all 3 zones, right? And those failure modes should be independent. So given that, you should be able to keep working with a zone offline. In fact, you should be able to transparently keep working. There shouldn't be a visible downtime if you automatically can fail to running on 2 zones rather than 3. So let's sort of work through this scenario and see what kind of hazards and what's likely to happen in practice. So let's say this zone is offline for some reason. Let's say there's a huge power cut or a hurricane or a flood or something, for whatever reason. So the system now has to detect that that's going on and notify the controllers that it's happening, but it should automatically reroute all the traffic, retry any requests that are in flight, and just keep going. So what's likely to happen is the control plane is likely to not clearly inform humans that everything is taken care of. And because there's going to be a huge flood of errors, you've just got 1/3 of your infrastructure just went offline. Anything that was talking to it's going to be complaining. You're going to get errors from the 2 zones that are still running, and probably errors from this zone as it goes down. So there's all kinds of things. Your system's basically going to be flooded with errors. It's not going to be clear what went wrong. And you can go through all of these sort of the STPA hazards on each of your sensors to say, well, what could actually go wrong in the failure mode with this particular sensor? Then there's the human control action. They shouldn't really need to do anything, but they're confused, they're working separately, they try to solve different problems, their tools are misbroken, misconfigured, all kinds of things. And you've also now got this flood of work is coming in, but the controllers are disagreeing, and their data's out of date, and then the zone fails, and the flood of requests and retries causes everything else to fail, basically. So this is the failover and fall over after failing over a problem. So you can see that it's very easy for the whole system to go down. Retry storms and things like that will break everything. So the way to deal with this is to do testing, do game days, because this is synchronous data replication. It should be consistent. You should be able to keep going after a few seconds. And if you regularly test it, that will work. But if you don't test it, and the first few times you try it, it's not going to work and it's going to take you out. So you can really guarantee that the first few times you attempt to do this, and back in the old days when I was working at Netflix, the first few times we tried this, we found all kinds of problems. And eventually we got this to be solid and we got it to be reliable and we dealt with all of the issues. And then we moved on to thinking about multi-region. So if we look at multi-region, it's a slightly different situation because the cross-region replication is asynchronous and eventually consistent. And most people do manually initiated failover between primary and secondary regions. And there's usually a visible downtime to do that, at least for the people in the region that's being failed over. In active-active, maybe the other two regions keep running, hopefully, and you just fail over the first one. So this is difficult to do. It's significantly more expensive, and if you haven't got really good operational excellence in place and you're in well-tested zone-level failure, it's really hard to figure out, do you have a zone failure or a region failure? You can get all these things mixed up. So most of the failure modes are the same. The difference is just on this. I've just picked out this one slide in that flow, because this time the human controllers have to initiate the failover rather than it being automatic. So they're going to disagree whether they need to do something or not. And quite often you get the same effect that when people redirect the traffic, if there isn't enough capacity in the remaining regions, then the incoming traffic can break everything. Particularly if there's a retry storm going on, there's a lot of work amplification happening. So how can we make all this better? One key thing is alert correlation. These floods of alerts have to be reduced to actionable insights. And there's some care and feeding needed to do this. There's some tooling in this space, Microsoft Big Panda, there's some other tools coming along. It's difficult to do this, and these tools need work to maintain them. And part of your game day is going to be to make sure that your alert correlation is working correctly and you are getting down to actionable insights. The other thing is you need a lot of headroom in your observability system. This is a problem, again, on very rapid, fast-growing systems. Like I remember back at Netflix, we were growing so fast, we kept breaking our monitoring tools. And if any of we had a failure, the extra traffic would typically push it over and break it. So you need to test that you have a lot of headroom or a way to damp down the floods and keep your observability system going under the impact of a big failure mode. And it may well be good to have more than one way to see the system. If you're using CloudWatch from AWS, it's already running at huge scale. It's unlikely to fall over just because your system has fallen over. If you're running a local instance of Prometheus or something like that, maybe that might have a problem. So you've got to figure out how do you scale these things. The other thing is retry storms. You want to prevent work amplification. There's usually far too many retries. I would cut retries to 0, except basically entry and exit points to your system or your subsystem. And then reduce timeouts to be really, really tight. You want to telescope timeouts so that a request at the edge is no longer being processed by the time the edge times it out. If you see what I mean, if you have the same timeouts through the system, there's lots of work going on for requests which have basically been orphaned. The people that made that request are no longer waiting for the response. So you need to truncate and do short requests in the system. So another good practice here is to do chaos first. Build your resilience environment before introducing apps to it. Build out a test environment, build all of your zone and any region, any testing you've got, and then add applications to it and have them sort of try to survive the, whatever you want to call this region, call it the jungle full of all of the chaos monkeys or chaos gorillas and whatever. But make it a badge of honor to have an app pass that test, try and gamify it so that teams feel proud that their system got through and other people feel like a pressure that they should also be able to get through. So the other thing we want to get to here is continuous resilience, continuously tested resilience. We need, just like continuous delivery has test-driven development and canary testing, you need the same kind of things for resilience. And that way you're building a failure mitigation into a well-tested code path. And I don't care if you call it chaos engineering. Some customers don't like the word chaos in production, so we'll call it continuous resilience in production and chaos engineering in test, or whatever the wording is. So sometimes you just need to get it done and avoid upsetting anybody with the idea that you might have chaos in production. And I think what we're seeing now as data centers migrate to cloud, these fragile and manual disaster recovery processes are getting automated. And we're moving from this scary annual experience to continuously tested resilience. So take a few questions. There's a paper I wrote about a year ago with, I contributed a section, Pawan and Agotri wrote most of it. There's a well-architected guides reliability pillar, some blog posts on this topic and on measuring response times and performance and on retries and things like that. And then you can find various slide decks on my GitHub account. And if you're interested in any of the book recommendations, I've got a link there.